Simple application of refraction of light here. Some of the application of refraction of light is that you can see when uh, there is a water here, fine, and you there is a stick. You will see if you put a stick inside it, or if you put a coin over here, and you will find that the coin, you see it from outside, it will not be seen there, it will be seen bit raised, as you have in this example here. So this is an example. This is what is an application where we can be able to use what, that is the refractive index. It happens because of the refractive index. How it happens? For example, there is a coin over here. So we know that we are able to see the thing when the light falls on it and it gets reflected, and the reflected light rays enter our eyes and we are able to see the thing. So when the light fall on this particular coin from any source, right, it will get reflected. So we have taken two rays coming from here, one here, another this way. Another is going straight, it will not get deviated. This is going straight, but it will get deviated. Why? Because it is from denser medium. This is water, it is a denser medium, and this is air, which is the rarer medium. So it will bend away from the normal, so it will slightly bend. So what we can do is we can produce that backward. Why? Because when we see something, okay, it looks straight to us. I mean, we can't see something which is like bent. Light travels in a straight line. So it means that the object, the coin which is actually here, is seen at this place, raised. So this place which we have is okay, is this depth from here to here. This depth is called apparent depth, and actual depth is this one here. So if I subtract the apparent depth from the real depth, then we get this distance, and that is called as shift. What do we call it as? Shift. You can see shift is equal to real depth minus apparent depth. Now, okay, and this is what I explained here. They have given in as a definition here: an object when placed in a denser medium, when viewed from a rarer medium, appears to be at a depth lesser than its real depth, and this is because of refraction. You can see the light has come here and it bent. If the light had not bent, then apparent depth would not have been created at all, and it will for sure bend. Why? Because there is a difference in the density of the medium there. So this is why there will always be bending of light, and as long as there is a bending of light, there will be the shift in the depth there. And this is the formula that we have, shift, which is OI in the case that we have here. OI, this is OI, if you see that, OI, and that is equal to real depth minus apparent depth. The other formula for shift is real depth into 1 minus 1 upon refractive index of the medium. So this is a medium, okay, maybe a glass, maybe water, right? So this has a particular refractive index. So the refractive index of medium with respect to air, because we are seeing in the air, this is the rarer medium, this is the denser medium. All of you can make notes of all these formulas, because these are something which we'll be using in the upcoming questions here. The second formula is, that is a refractive index. We know the formula, refractive index is equal to what is the refractive index equal to? That is OA, which is the, what is OA? OA is the actual depth, right? Real depth upon, that is apparent depth, AI, right? This length. So the another formula for refractive index is, in this case, is real depth upon apparent depth. Remember, you can make a note of all of the formulas. That is, refractive index is real depth upon apparent depth. So make a note. Then apparent depth will be what? Apparent depth will be real depth upon refractive index of that medium. So just exchange. This will come here and this will go there. Is that okay? So you will have the formula, these three formulas which you have, you keep it, and we will be using it for upcoming numerical Senate. Then the shift that we are talking about, this shift can be more, can be less, right? Means that shift, that the object which was actually here is seems to be seen here, it has been raised. So this shift, the shift can be more, it may look like over here, or it can be look like over here. So the shift can be more or less, it depends upon the refractive index of the medium. You can see apparent depth, right, is real depth upon the refractive index. So if you have the real depth as say 100, fine, and refractive index is 10, then the apparent depth will be 10 in it. Okay, 100 upon 10. If the real depth is 100 and the refractive index is 20, then the apparent depth will be 5 in it. So does it depend upon that? Yes, you can understand. So because of the formula, you will be able to know this. Now coming to the thickness of the denser medium. More the thick, for example, if this was not bending from here, it was bending from this side. This is the thickness. It will go straight until here, and then from there it will go away from the normal. So it will bend more. Is it clear? You produce it, it will be more. So it depends upon the thickness of the medium also. It depends upon the color of the light, wavelength of the incident ray. If the ray of light which is coming as a red, so red has got higher, bigger wavelength, so it has got higher velocity, so it will bend least, right? It will bend least of all the color. And you take the violet, it will bend most. So the one which bend the most will have more shift. The one which bend less will have less shift. Shift means this apparent distance here, right? I mean shift in that, you know what is shift. So it depends upon the color here. So which one will bend more? Violet. So violet color is incident, then yes, it will show it has been raised to a higher distance. For example, if the ray of light is coming as a red color, then the shift may be here. If it is violet color, the shift may be here until this point. You can see the shift depends upon the refractive index, sorry, depends upon the incident color of the incident ray. Is that okay? Next comes here some consequences of refraction of light that we have already seen in the video earlier. Same thing, I'll just make you revise that. Now, you know, say star you must have seen twinkling in the sky. That is because of refractive index of air with temperature. What happens in it? Say air do not have same density throughout. Okay, if we are on the earth here, this is the earth surface, and we are standing here, and there is a star from very far away here. So what happens? The ray of light is coming. Okay, if it is coming like this, you know, this is the rarer or rarest medium, then this is slightly denser. So okay, we can write the density as such here. This is the highest density, density 3, density 2, and density 1. Now if the density is less as compared to it, so it will bend less, it will bend here, but not that much. Density is slightly more, it will bend more. Density is more here, it will bend more, right? Got the point? So I could not draw that properly, so I'll just draw it here. So it will bend like this. Here it will bend more. So if a person is over here, he sees this star which is coming like that. Can you see that? But for him, everything looks straight. So if you draw a straight line, so where will the star be? So for him, the star would be where? The star would be here. Just one second. The star would look straight, so I need to just produce that line here. See, this is straight, so for him the star would look where? The star would look here. Got the point here? The star will look over here. Now actually the star, this is the actual place of the star, and this is the apparent. Why? Because the bending of light is happening. Here it bends less, here it bend more, here it bend the most. And so if you draw the straight line from there, it will go and see, okay, the star is located here. Star will be seen at this place, which is not the actual. This is the apparent position of the star. This is the actual position of the star. Got the point here? When I say actual, so which is the actual? This is the actual here. And this is apparent. Means at this place it is not. Clear? Now what happens? Remember, the density of the atmosphere is not constant throughout. Is not fixed that it will always be density D1. It will always be density D2 and D3. No, it keeps on changing. Why? You know that because hot air rises, cool air takes the place. Sometimes the temperature of the atmosphere is different, right, depending upon the kind of gases it has received, means hot or cold. So the density is dynamic here, it's not same, it keeps on changing. So if the density is changing, sometime what will happen here, this become more denser, right, and this become very high dense, or this maybe become less dense, this become okay, further less dense. So what will happen if they become less dense, then the apparent position of that star will not be here, it will looking somewhere here. Sometimes it will look here, sometimes it will look here, sometimes it will look here, sometimes it will look like that, right? Or maybe it can be something like this, it can sometimes it looks here and sometimes it looks here, because it is changing. So the same star, okay, once seen over here is seen this place, sometimes seen this place. Now what happens at that? So it will look like as if the star I was seeing now here is no more seen, right? Are you getting the point here? You see that, so if since it is a very far away place, so that distance I have drawn here is this much, but actual the distance will not be that much, it will be here, it's like very close to it. So I would say, like, say for example, it will be like this. Okay, I'll draw some other color, okay, black. So it will look as if it is here, and the next point of time it will look as if it is here. Can you see that? So almost at the same place, right, it is here, 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 right? So for us it will, if you see that continuously, it will look like twinkling, it will be twinkling. Is that okay? Now sun is seen few minutes before it rises. Again, there is a phenomenon which you must have seen in the video. This is the atmosphere of the earth, right? And the sun is over here. The ray of light will go from where? This place. The moment here, the moment it passes from this denser air, it will slightly bend. So the person over here can see the sun, it is bending, the bending of light goes this way. This is the atmosphere, it will have some density, it will bend. So the person over here will see this sun where? It will see the sun at this place. Is the sun at this place? No, the sun is over here. This is the actual place. This is the apparent place. So what is the difference? This is about something like some 8 minutes altogether, right? 4 minutes each. So okay, he sees the sun which actually is not over here before it rises. So for him the sun would rise, had there not been the atmosphere, the person would have seen the sun for the first time at this point of time, say for example 6 o'clock, but he sees it at 5 o'clock and 56 minutes. When it was, where was the sun then? The sun was at over here, this place. 5:56 is less than 6 o'clock. It was here, not there. So he sees the sun 4 minutes earlier, right? Why? Because of this bending of light. Had there not been atmosphere, then he would have seen the sun exactly at what? 6 o'clock. But he's seeing it at 5:56, 4 minutes earlier, because the light ray bent. Now same goes for sunset. In the sunset, sun has come over here, so it will go straight, and it will from there, if you draw the normal, it will bend towards it. Okay, but actually the sun has already set. For him the sun will look like it is setting here, but sun is not here, sun has already set. So this is again 4 minutes. So 4 minutes here, 4 minutes here. I think whatever the time that he has, I'm not yet confirm about the time, but yes, it will be early. Fine, few minutes longer sun sets. Okay, for the person it will look like the sun is over here, but actually the sun already has set. Is that okay? If the sun sets at say 5 o'clock and 30 minutes, right, but the sun has set, it's still showing here, this will be at 500, not 5, this will be at 5:30, it has to be there, but it's showing at 5:34. Okay, so 4 minutes sunset extra. Okay, so we can say this area is lit up by the sunlight for 8 more minutes every day. An example, maybe the figure I'm giving you may not be correct. Now, the coin kept in the vessel is not visible seen from below the edge of the vessel. It can be viewed from some position when water is poured into the vessel there, right? This is also happening because of the refraction. A print appears to be raised when the glass, if you have something written over here and you have a glass slab on it, you will find that this particular R will be okay, the letter will be seen a bit raised in it. Fine. So that is the because of the refraction of light. Is same concept of the coin that we can use in it. A piece of paper stuck in the bottom of the glass appears to be raised. If you have some paper over here, you keep it, it will look like it is over here raised because of the same. Tank appears shallow than its actual depth. If it is a tank, like it looks as if like it is very near to the surface, but actual depth is much more. We have seen that. A person leg appears to be shorter when standing in the tank. If you find there's a person is standing in the tank, so his body is over here, his legs are there, you will find that the legs looks a bit smaller in that case. Why? Because of refraction of light. So these are some of the application of refraction of light. Fine, already have done in the video. I just gave you these formulas for so that we can be able to solve the numericals on it. Okay, this is only for the purpose of numericals. I gave you this formula and a bit of understanding. So in the next video I will be showing solving some example numericals for you.